It won't be proved wrong. Right, okay, so half-value thickness. This is very similar to half-life. Half-life was the length of time it takes for activity of a source to half. The half-value thickness is the thickness of absorber that makes the activity of a source half. Okay? So half-value thickness is the thickness of an absorber. So an absorber of radiation, for example, lead absorbs everything. Then you get paper, which only absorbs alpha, and aluminium, which absorbs beta. The thickness of an absorber that would reduce the activity of a source by half. Now, by an absorber, I'm just going to write that down here. Now, absorbers come in three different forms depending on what you want to try and absorb. Lead will absorb gamma, beta, and alpha. So lead absorbs, as a symbol for gamma, plus alpha, plus beta. Aluminium would only absorb alpha and beta, and paper would only absorb alpha. Remember, you've also got so many centimetres of air as well, but generally they are the absorbers. Air can be absorbed as well, but generally they are the materials that we deal with: lead, paper, or aluminium. And that's what I mean by it. So the thickness of lead, the thickness of aluminium, the thickness of paper. It could be any material, concrete or whatever, but they're the common ones that we talk about.
What gamma was the UI?
It is meant. That's a symbol for gamma, but you can. It does look like a Y if you make that hole at the bottom really small.
Very
Tightful.
See if you wore like a paper suit, right, and like walk around a nuclear place, would you not get as much then?
If you wear clothes, you won't get as much.
A
A paper suit. No, the clothes you're wearing just now are a better absorber than paper.
And aluminium.
No, I mean like if you wore a paper suit over your clothes.
Right, no. What you don't get is that over your clothes, yeah, you wouldn't get alpha.
If you wore a suit of lead.
Alpha only lasts a few centimetres in air. So alpha's the most dangerous. But as long as you don't stand too close to the alpha, you're fine. Do you know what I mean? So beta travels a bit further in air. So beta wouldn't get absorbed by paper. So beta would be absorbed by your skin, or be absorbed by thick muscle tissue.
So beta's the danger one.
Well, not really, no, because it doesn't have. It's not going to cause you as much damage because it needs quite a lot to absorb it.
So how do people get like radiation sickness for like things that are like?
Because the radiation goes into the atmosphere.
Because the amount of activity it's getting, like loads of it coming off. We're talking about one little alpha particle. I'm talking about a really highly radioactive source.
But it's still just so radioactive, and then.
Like gamma goes through you, okay? But if there was so much gamma going through you, you would get radiation poisoning.
Do you not get radiation poisoning if you fly too much?
Yeah, because you get gamma rays hitting you. So the point is, gamma passes right through you. It does get ever so slightly absorbed. But, so it's considered the least dangerous. However, if you get loads of it, it will cause you damage. Does that make sense? Just like in.
Like
Too much ice.
Too many apples in your teeth.
Too many apples and you die. Aye, okay.
You know, if you eat a polar bear's liver, you get vitaminosis.
Vitaminosis.
Mr. Racket in one English.
Aye, he's full of.
Alright, anyway. Half-value thickness is the thickness of absorber that would reduce the activity of a source by half. So what we need to know is describe the principles of a method for measuring the half-value thickness of an absorber. Essentially, set up a source, set up some absorber, and set up a Geiger-Müller tube behind it. And just change the thickness until you get half the value. Or measure the activity at different thicknesses and calculate what the half-value thickness is. So let's just quickly do that. So a method for this would be.
This was one sentence.
What's that?
Just one wee sentence.
I need to write this box.
Okay.
Is that not this diagram?
That's the diagram at the top of your notes. You do not need to copy this in your jotter.
Oh, we doing?
You don't have to copy this method in your jotter.
Alright.
It's at the top of the notes on page 42.
Ah,
Okay.
Yogurt.
right? So you've got the source, you've got the absorber here, and you've got the Geiger-Müller tube here. You don't need to copy this in because it's in your notes. Now all you're doing is changing the thickness of this absorber, and you're measuring the activity you're getting out. And if you take loads of readings for different thicknesses, you can work out the half-value thickness. Now, so highlight the little diagram, and you also need to know the graph. The graph is how the thickness of lead compared to the count rate, which is your activity. You need to know what the graph looks like. So your graph from the notes on page 42 looks like that. Now that is the same type of graph as you would get from a half-life graph. Activity down the side, and along the bottom you've got the thickness. You must be able to identify that graph. It could be a multiple choice graph. Activity on the left hand side, thickness down the bottom. Okay? Right, so we've been able to sketch a graph, describe the principles of a method, that was in the diagram, carry out calculations, we haven't done that yet, and state that the equivalent dose rate is reduced by shielding or by increasing the distance from our source. Right, so that's the last thing. The dose rate can be reduced by providing shielding or moving away from the source. And that's on page, pretty sure that's on page 43, the last page. Okay, so move away from it or put an absorber on, really to reduce the amount of radiation you're getting. Okay, so that's us finished the higher course.